This is Daniel Cusberry, and in this lecture we're going to keep graphing functions. In particular, we're going to look at linear functions. And so there's a few techniques that we can learn that apply specifically to linear functions that are going to make things a little bit smoother and maybe a little bit easier, or at least a little bit quicker when we try to graph them. And so this first technique, we're going to call it graphing using intercepts. Okay, the way this works is we're going to consider that most lines on a graph end up intersecting both the x-axis, this is the x-axis, and the y-axis. So anytime I draw a line straight through here, it's going to cross one or both of these. And the way I can do this is I can notice that there's going to be some point that crosses the x-axis, and that point is going to have an x-coordinate, like 1, 2, 3 or something, but it's not, the y-coordinate is going to be 0. So if it hits the x-axis, it's not going up or down at all. The y-coordinate's got to be 0. So there's going to be some sort of thing, point on that line that looks like this, something comma 0. So like maybe 1 comma 0 or 2 comma 0. Also, if it crosses the y-axis, there's going to be, the y value is going to be like 3, 4, 5, or 6, but the x-axis, it's not going left or right. The x value is going to be 0. It's not going to be -1 or 1. It's going to be 0 because it's on the y-axis. So I'm going to have some point that looks like this, also 0 comma something. So what I'm going to do is I'm going to try to find both of those points, the points where x equals 0 and the point where y equals 0. And if I have those 2 points, I can just connect them and then draw a line, and that's kind of the nice thing about how this method works. So for the first one, let's take this equation. Let's let x equal 0. So the first time I do this, I'm going to let x equal 0 and find out what y is equal to. I can do that. I can just pick an x value and see what the y value is. So this is 4 times 0, or 0. So this is really 6y is equal to 12, or y is equal to 2, which means that my point here is x is 0, y is 2. So that's 1 point on this graph, 0 comma 2. So that turned out to be my y-intercept. And then I'm going to also let y equal 0. So 4x plus 6 times 0 equals 12. And then see what the x value is. So this time I'm picking out a y value, but I don't get to pick the x value. I got to see what the pair is. So I pick y is 0 and see what x is equal to. That's 0. I get 4x is equal to 12, or x is equal to 3. So my ordered pair then is x is equal to 3. Y I already said was 0. So I picked one, and then the equation gave me the other one. So now I have 2 points. I've got 0 comma 2, and I've got 3 comma 0, which is right here. So I found my y-intercept, I found my x-intercept, and I did those by letting each of those variables equal 0 and solving the equation for the other variable. And so now this is my line. Kind of missed, but in a nutshell, that's it. So this is a nice method because it actually didn't take very long, and I got to plug 0 into the equation, which is really nice because when you multiply things times 0, the math gets a lot simpler. It just goes away. So this is one method. I want to talk about slope, and we're going to get to another method. So we're going to use the slope of a linear equation to graph the line. And so slope we define as the change in y over the change in x. So how do the y points in the ordered pair change, and how do the x points in the ordered pair change? It's the ratio of the change in y over the change in x. We also call it rise over run. So how does the vertical change relate to the horizontal change? So rise over run. And to do this, if we have 2 points on the line, any 2 points on the line, this is kind of cool. You can just pick out 2 points that you know are on the line. We'll call it x1 comma y1 and x2 comma y2. Then you can calculate the slope by this formula right here. So y2 minus y1 over x2 minus x1. So you got 2 points, you can find the slope. And so it's not a terribly hard thing to do. Here's an example where I have 2 points. And so this is my x1, y1, this is my x2, y2. So my slope then is going to equal, we're going to start calling this m, is going to be equal to y2 minus y1, so 2 minus 1, over x2 minus x1, 2 minus -3. And this ends up being 1 over 2 plus 3, which is 5. So that's my slope is 1 over 5. So if I have any 2 points on a particular line, it doesn't take me that long to find the slope. In fact, I just have to use this formula. So with that, let's talk real quick about slope-intercept form, and we're going to use that to end up graphing a line. So this is the slope-intercept form of a linear equation. Notice that the linear equations themselves always have an x and a y in them, or for the most part have an x and a y in them. And so in this form, the y is completely by itself on the left side of the equation. There's nothing here, nothing multiplied by it or added to it, just the y. And then on the right side, you have something times x plus a constant. We'll call that b. Okay, that b we're going to also call the y-intercept. It's a cool little thing that happens. And any number that's multiplied by the x, or multiplies the x with the x, we'll call that the slope. So the slope is going to be m, the y-intercept is b, so we call it slope-intercept form because it has the slope and the y-intercept. So if y is by itself on the left side of the equation, then the equation's in slope-intercept form if it's linear. Okay, so here's an example. Y is equal to 2x minus 4. So this is a linear equation, and y is by itself on the left side of the equation. So that means it's in slope-intercept form. That means we have the slope. This is the slope. We'll call it m. And we have the y-intercept, which, notice since there's a plus sign here, we got to consider this negative sign. So this whole minus 4 is going to be the y-intercept. So if there's a plus, it would be 4 would be the y-intercept. But since there's a minus, it'll be minus 4. So I have the slope and I have the y-intercept. So I know that where it crosses the y-axis is at negative 4. This is a really handy form because all I saw was a minus 4 there. I knew it was in slope-intercept form. And that allowed me to put a point on the graph already. Now, the other thing I can do is I also have the slope here. The slope is 2. And remember that my slope is also equal to a rise over run, how much it goes up over how much it goes across. So if I think about 2 as the slope, I can also think about 2 as a fraction, 2 over 1. Those are the same number. My rise is 2 and my run is 1. So what I've done is I've taken my slope, I've written as a fraction because it wasn't obviously 1, but 2 over 1 is equal to 2. They're the same number. This means that from any point on the line, if I go up 2 and I go to the right 1, I found another point on the line. It's a really cool thing. So this is how I'm going to graph this function. I'm going to start at the y-intercept because I know that's on the line. I know it. That's right there. And then my slope tells me I can go up 2, rise 2, and then go to the right 1. That's the bottom. Go up 2 into the right 1, and that point's on the line. And from this point, I can go up 2 into the right 1, and that point's on the line. And so on. I can go up 2 to the right 1. I can keep doing this until I run out of paper. And even then, I could probably keep doing that if I wanted to. But there's also a point down here that follows the same sort of pattern. And now I have a line. I have a line with slope 2 and y-intercept 4 based on this equation here. So the slope is 2. From any point on the line, I go up 2 to the right 1. The y-intercept is 4 because it crosses the y-intercept, the y-axis at 4. So this is my line. And I use the slope-intercept form to graph it. This is a really cool method of doing it because I didn't have to go and find a bunch of ordered pairs and points and plot them. This is a lot faster once you kind of fiddle around with this equation some and learn what these things mean. So here's another example. We're supposed to graph this linear function using slope-intercept form. And anytime you want to do this using slope-intercept form, you should look at your function and say, is it in slope-intercept form? Well, y is not by itself on the left-hand side, so it's not in slope-intercept form. So we got to do a little bit of work first to get y by itself on the left-hand side. We're looking for this form, and it's just not there yet. But we're good at algebra. We can do something about that. So let's work with this equation and try to get y by itself on the left-hand side. We'll just solve for y. So I'll start by subtracting 2x from both sides, and I end up with 3y is equal to negative 2x plus 5. I just subtracted it from both sides, so it went away over here. Now it's over here. It's negative. And now I want to get y by itself, so I'll divide this by 3. I'll divide all that stuff by 3. I end up with y by itself, and then here I have negative 2 divided by 3x, and I have 5 divided by 3. So I just divided everything by 3. And now I have slope-intercept form. Do you see it? There's the m there, and there's the b there. So that didn't take a whole lot of work, but once I get y by itself, the slope-intercept form kind of pops out. So whatever number is attached to the x is the slope. Whatever constant is in the equation is the y-intercept. So I can start graphing this by graphing 5 over 3. It's not going to be very easy because it's not on clearly on the grid, but 5 over 3 is a little bit less than 2. It's right around here somewhere. And from here, I can use this slope to graph the rest of the points. So this says from any point on the graph, my rise is -2 and my run is 3. So from any point, I can go down 2. My rise is -2, so that's down 2. And my run is 3, so I go to the right 3. Just assume this is going to the right each time. So I'm going to go down 2 and to the right 3. So from here, I'm going to go down 1. This is a little tricky. 1, 2, so right around here-ish. And to the right 3. 1, 2, 3. So it's going to be kind of in between stuff right here. So that's what I did. I go down 2 to the right 3 because that's my slope. So from here, I'll do the same thing. I'll go down 2 and to the right 3. So there's some point over here. Also, this pattern continues. So I can do like the opposite things to get the points over here. I can go up 2 and to the left 3, just doing it backwards. And I'll go up 2 and to the left 3 and get this one. But notice I haven't cheated or anything because I started going up and left, because from any point on this graph, if I go down 1, 2, and to the right 3, I still have a point on the line. So this all works out. And notice if I were to perfectly draw a line through here, which I'm doing my best. Let me try again. If I were to perfectly draw a line through here, nope, still kind of missed. It would go straight through those points, and that makes it a linear equation. So we've done this work right, and it's pretty good. I'm just not very good at drawing straight lines. So that's how you graph things using slope-intercept form. You got to make sure first that it's in the form, and then you can put the y-intercept on and use the slope to find the rest. Okay. There's a few other kind of special lines. We'll call them horizontal and vertical lines, and so we kind of know what those words mean already. But their equations look a little bit unique. So let's look at this first equation. This is the equation x equals 4. Notice it doesn't look like slope-intercept form or anything. Like you don't have a y in there or anything like that. All you have is that x is equal to 4. So the way we should interpret this is that any point on this line, x is equal to 4. Okay, so that means if I were to just go out and write a few points on this line, and I'm just going to kind of pick some values. For any point on this line, x is equal to 4. So that means whatever ordered pair I want to make up, x is equal to 4. So when y is equal to 3, x is equal to 4. When y is equal to 4, x is equal to 4. When y is equal to 5, x is equal to 4. And if I were just to come up with a few more, like if y is 0, x is 4. If y is -1, x is 4, and so on. You kind of get the idea. For any point on this line, x is equal to 4. So if I think about plotting these, 4, 3, 4, 4, 4, 5, 4, 0. And like you notice I could have kept going and going and going, but notice what kind of line this is. This is a vertical line. This line just does this. It just goes straight through 4. Kind of made it crooked. Sorry. This is a vertical line. Okay, I didn't know it was a vertical line by looking at this, but now that I can see, oh, okay, if the equation is x equals 4, that means there's going to be a vertical line going straight through 4 on the x-axis. That's kind of cool. Or you can think about it as every point on the graph is going to have an x-coordinate of 4. So here's something also interesting. We have the equation y is equal to -3. So that means any point on this line, y is equal to 3. So if x is -1, y is equal to 3. If x is 0, y is equal to 3. If x is 4, y is equal to 3. If x is -5, y is equal to 3. So we have a similar phenomenon going on here. We have -1, 3. We have 0, 3. We have 4, 3. Oh, there's a point right there. And we got -5, 3. And so notice what's going on is we're actually graphing a horizontal line. So when I have an equation that looks like y equals a number, and that's it, it's a horizontal line. Because all the y coordinates are 3. Oh, I'm sorry, that's a -3. Let's just make that +3. I'm cheating. Okay, so y is equal to 3. So that's that line right there. Cool. So anyway, when you're looking for horizontal, or when you're looking at these particular equations, x is equal to something, y is equal to something, it might be helpful to just memorize that these are horizontal lines. or these are vertical lines, these are horizontal lines, but what I like to think of is, in this case, all the y values are 3, so it's horizontal. In this case, all the x values are 4, so it's vertical. These aren't very hard to graph at the end of the day. You just don't want to get them switched. Let's look at an application problem. So here we have a situation, there's just some data that's been used, and it's been plotted on this graph. This says, as we age, daily stress and worry decrease, and happiness increases according to an analysis. 340,847 U.S. adults ages 18 to 85 in the journal Proceedings of the National Academy of Science. So here's some proportions of people reporting stress based on this age and based on this age. And so right now we've only got 2 ages. We've got age 22 and we've got age 62, and these are the percentage who report they're stressed. So what we've done is we've taken this data and we put it on a coordinate plane where the x-axis represents the age and the y-axis represents the amount or the percentage that people who respond they're stressed. So there's the 22 point. So at 22, 49% are stressed. There's the 62 point right around here. At 62, 29% are stressed. So what we've done is we have 2 points, and now we have a line, and we can talk about the rate of change from this line. So the first part of this question says, go ahead and find the slope of the line passing through the 2 points. That's not hard. Let's call it x1, y1, x2, y2. In this case, our slope is equal to y2 minus y1 over x2 minus x1. This is going to be negative 20 over 40, which ends up being negative 1/2. Or we can, I think for the purpose of this problem, we'll call this negative 0.5. So the rate of change is negative 0.5. So every time we go, we can maybe interpret this rise over run. Every time we move on this, if we go down 1, we're going to go to the right 2. The rise is negative 1, the run is 2. So down 1 to the right 2. And this is kind of how we would interpret this rate of change in this context. So this says for each year of aging, the percentage of Americans reporting a lot of stress decreases by 0.5%. So for each year, it's going to go down by 0.5%. So you go down 1 over the right. So the rate of change is 0.5%. So we're interpreting slope as the rate of change. It's 0.5% per, you can say per age year or per year of age. I'm just going to say per year. You know, we're talking about age. So for each year in your life, your rate, the percentage of Americans reporting stress goes down by 0.5%. So I guess as the population gets older, they get less stressed by 0.5% each year or something like that. So we'd interpret that slope as some kind of rate of change of this per that, because it's a fraction. All right, let's do a couple modeling things too. So there's some advantages of using slope-intercept form in contexts that we can describe as a linear equation. And I'm just going to go ahead and demonstrate this with these 2 examples. The directions say find a linear function in slope-intercept form that models a given description. So remember, our slope-intercept form is y equals mx plus b. And we're going to interpret slope as like a rate of change because it's kind of been how it's been working this whole time, this whole rise over run. You know, every time we go to the right, something is going up or down. So this is our rate of change, this m. And then b is just going to be some constant that plays a role in our situation. So let's just see this situation and see if there's anything that feels like a rate of change and feels like a constant. Now, the part of the direction I didn't read, I need to read real quick. Each function should model the percentage of the particular high school grade, p of x, so that's what p of x is, the percentage of that grade, of students entering college x years after 1968. So in this case, like if x is 1, that's going to be 1 year after 1968, so 1969. When x is 1, it's 1969. If x is 2, it's 1970, and so on and so on. So here's an example. In 1968, 18% of the grades for students entering college were A, including all these variations of A. This has increased at an average rate of approximately 0.725% per year since then. So what this is saying is in 1968, then we have 18% of the grades were A's, and then it increased by this. So if we're looking at these numbers, I see two in particular numbers. There's an 18% and there's a 0.725%. One of those is going to be our rate of change. And it actually kind of tells us which one of these two numbers is a rate. This says it's an average rate. So this 0.725 is the rate of change. So if we're trying to write an equation in slope-intercept form, let's use the 0.725 as our rate, which is the part that's attached to x. So the m is the rate, which is this thing right here. So as each year goes on, it's going to increase on average by 0.725%. So now what we also need, though, is we need the y-intercept, and we need to know what that is. And remember, the y-intercept is the value where x is equal to 0. Remember, all the y-intercept, x is equal to 0, and then that y would be like, 1, 2 would be like up or down on the y-axis. So we're looking for a situation where x is equal to 0, and then what's y? So whatever this y is our y-intercept. And let's look at our context again. X is the number of years after 1968. So when x is 1, we're talking about 1969. When x is 0, we're talking about 1968. So if this situation is dealing with 1968, then we're already dealing with a situation where x is 0. That makes sense. So since we're talking about something in 1968, we're talking about a situation where x is already 0. So in 1968, 18% of the grades for students are an A. This 18% is going to be our y-intercept. And that's because we're talking about a particular year where x is 0, namely 1968. So we're going to use that 18% as our y-intercept. Okay, let's look at this next one and see if it works in a similar way. So in 1968, 23% of the grades for students entering college were C, any variation of C. This has decreased on average at an average rate of approximately 0.45% per year since then. So we already have an average rate here of 0.45%, but this says that it decreased by 0.45%. So why don't we let m in this case equal negative 0.45? So that number attached to the x is now a negative rate, negative 0.45, because we're decreasing here. And then for the y-intercept, we need a situation where x is 0. What's the y value? Well, here again, we have this 1968. It's telling us what's going on in the year when x is 0. Remember? So when x is 0, the percent of students with grade C is equal to 23. So this is going to be our y-intercept. This is the y value when x is 0. Cool. So that's how we're going to use slope-intercept form to help model situations. We're going to need to find the rate, which is m, and we're going to need to find the constant value when x is equal to 0, and that's going to be our y-intercept. So in this case, it was the 18 and the 23. So I hope that's enough to get you started on some of these questions. A lot of it is just graphing using slope-intercept, but the modeling questions, these forms, these intercepts, and the slope-intercept forms are going to come into play, and it's going to be really handy.